My great pleasure to introduce Bivas Saha. He did his PhD at Purdue and then went on to do his postdoc at Berkeley, and he is currently based in Bangalore. So please go ahead.
Thank you so much for the introduction. Let me start by first thanking Professor Tony Cheetham for giving me this opportunity to speak here. So the title of my presentation is Emergent Pathways to the Metal-Insulator Transition. And in this presentation, I primarily will focus on the role of magnetic stress, potential fluctuation, and confinement in metal-insulator transition. But before I go there, so I'm Bivas Saha, so I'm an associate professor at JNCSR, and our core expertise is basically lies in growth of thin films and heterostructures with ultra-high vacuum methods such as molecular beam epitaxy and magneton sputtering. And these are some of the research projects that we are currently having. Light matter interaction, basically we make nanostructure objects to control light matter interaction and develop devices. Recently, we are also working on quantum materials based on antiperovskite nitrides. We also work on phase change materials, and that is what I'm going to talk about, metal-insulator transition. And we do a lot of first principles simulation also to explain the material properties. Now, before I go to this metal-insulator transition, let me just quickly highlight one small topic which is very relevant to rack. So this is a passive radiating cooling that we have been working on for some years. And the idea of this project is very simple, is that in summer days, because of the solar radiation, almost all surfaces, external surfaces heats up. And this heating can be more than 10 to 15 degrees C compared to what the indoor environment would be. So for some time, after some trial and error, we have now developed a paint, which is a solution processed radiative cooling paint, primarily made of MgO nanoparticles and PVDF, which really shows a large surface temperature reduction of 6 to 9 degrees C due to the fact that it has low solar reflection, a very high solar reflection, very high thermal emission. At the same time, it's hydrophobic, stable, and scalable. So it's a white paint. And very recently, over the last 1 year, we are doing the outdoor test of this paint in Ras Al Khaimah in AU rack about maybe 30 minutes from here. So let me go back to the original topic that I am supposed to present, and that is the metal-insulator transition. This is the basic slide, and I'm pretty sure most of you have seen this. So metal-insulator transition basically refers to the fact that you have, if you look at this, this plot, resistivity versus conductivity, resistivity or conductivity of different materials. You have this metal in the right side with a very high conductivity, insulators in the left side, which has low conductivity, is some material. And obviously, they're characterized with metals in case the overlapping valence and conduction band. In case of insulator, you have a separation between valence and conduction band. But some material which, when you apply an external perturbation like temperature, pressure, or electric field, undergoes a metal to insulating transition with at least 3 to 4 orders of magnitude change in resistivity. Now, this metal-insulator transition invariably also accompanies by structural transition and also magnetic transition in most materials. Now, if you really go back and look at the history of metal-insulator transition, the first example of metal-insulator transition is basically the Verwey transition in 1939, where iron oxide, Fe3O4 or magnetite, undergoes an insulating phase at low temperature to a metallic phase at high temperature at around 125 Kelvin, accompanied with a structural transition. But the most prevalent example, or most the famous example of metal-insulator transition is, of course, vanadium oxide, invented by Morin from Bell Labs in 1959. Vanadium oxide undergoes a low-temperature insulating phase to high-temperature metallic phase at around 60 to 70 degrees C. And the structure also changes from a monoclinic to a tetragonal phase. Now, there are many mechanisms of metal-insulator transition that has been proposed in the last several decades, but I think none of them are complete unless a specific mention of 3 mechanisms invented by Neville Mott, P.W. Anderson, and Peierls. So in one case, the Mott transition is basically when you have D bands of transition metal near to the Fermi energy splits because of the electron-electron Coulomb repulsion, giving rise to upper Hubbard band, lower Hubbard band, and this is the metal that causes the otherwise metal to act as an insulator. In case of an Anderson transition or Anderson localization, you have defects in your crystal, defects in your material, where electron wave or any type of matter wave in their respective transport domain basically coherently backscatter, leading to a seizure of the propagation. So that's basically the Anderson transition. And in case of Peierls transition, that is basically the lattice distortion. In some material, for example, in charge density wave or similar material, because of the lattice distortion, you have unit cell doubling that leads to a metal to some insulating transition. And the applications of metal insulator transitions are manifold. People have designed, and currently research efforts are also going on to develop smart windows, because with a large change in resistivity, you can also change large changes in the reflection and the transmission behavior. The fact that metal insulator transition happens gives rise to 10 to the power 5 to 10 to the power 4 to 5 orders of change in conductivity, but at the same time, the transition happens from picosecond to nanosecond time scale, also have been utilized to develop now real application RF emitters, microwave switches, so on and so forth. And these days, there are also a lot of work going on in utilizing metal insulator transition for brain-inspired or neuromorphic computing. Now, let us look at if you really look at what are the materials which exhibits metal insulator transition. So this is the x-axis, which is the temperature at which the MIT takes place. And these are all the material which we get found till now. And as you can see in this picture, most of the materials that show this MIT are the part of oxide family of materials. So oxides are mainly the material for MIT, but there are also some sulfides, there are also some phosphides, there are also some selenites, and this is, I'm referring only when you drive the metal insulator transition by changing temperature. You can also drive metal insulator transition by pressure or electric field change, and some of the oxides shows all three possibilities. Some of the organic semiconductors show all three possibilities. Phase change material has either show pressure-driven or field-driven. So some combination of this, but if you look at this entire curve very carefully, there is not even a single nitride material in this list. So that's quite unfortunate, because nitrides have really emerged as a very important class of material. 30 years back or 25 years back, if we talk about nitrides are only used as a coating material in watches and drill bits. Of course, in 90s and late 2000, this changed with the invention of gallium nitride, with the gallium nitride LED that changed our society in many different ways. But today, if you look at the research landscape, nitrides are used in many different applications. For example, defects in hexagonal boron nitride used for single photon emitters. So you have superconducting niobium nitride being used for Josephson junction, power electronics, thermoelectrics, and so on and so forth. So nitrides really offer a wide spectrum of application because it has a wide spectrum of electronic properties. For example, you can find a very good metal in nitride, titanium nitride, very good insulator like boron nitride or aluminum nitride, and a very good semiconductor like gallium nitride also. So it really gives you a lot of flexibility in developing devices. They are most of these nitrides are stable at ambient condition with a very high melting temperature, so that allows you to make devices, in addition with their corrosion resistance, mechanical hardness, and toughness. So in this work, in this presentation, what I shall show is our work over the last 2 to 3 years on basically metal insulator transition on three emerging nitrides. So one is the magnetic stress-driven MIT at chromium nitride. One is electron confinement-induced MIT and plasmonic breakdown in metals in hafnium nitride. And the third is the potential fluctuation-driven quasi-classical Anderson transition. So let me start with the first one. Now, although I showed you the last curve where there was absolutely no nitride, but if you really look at literature very carefully, there is actually one nitride, and in a very one or two reports in the literature would show that chromium nitride actually undergoes a low temperature metal to high temperature insulating phase, accompanied by an antiferromagnetic ground state at low temperature to a paramagnetic ground state at high temperature, and the structural transition also orthorhombic to rock salt. The only problem of this is that although the first evidence of it was shown long back in 1959, after that, there was a long debate whether this metal insulator transition really occurs or not. So here's a paper by John Goodenham suggesting there is a transition, but there was immediately, within few months, there was a question. And in case of thin film or heterostructure, you see there is always a debate whether the transition really exists or does not exist. So when we started working on this material, the first thing for us, of course, was to get the transition or to get the reproducible transition. And what we realized is that although chromium nitride does show a metal insulator transition, it's extremely sensitive to its stoichiometry, very similar to VO2. VO2 has many different phases. Unless you hit the M1 VO2 phase, you will never get a 3 to 4 orders of magnitude transition. Similarly, in this particular case, unless you reach a stoichiometry of 1:1, you will never get a metal insulator transition. So this is what is shown there. When you grow them at a high growth rate, because of the formation of secondary CR2N grains, they don't show any transition. It's only when you reduce the growth rate to a much lower rate of 1 nanometer per minute, you see the crystal looks perfectly epitaxial, single crystalline, and they almost invariably or reproducibly show this metal insulator transition. So now if I look at and compare the metal insulator transition in chromium nitride with VO2, so VO2 shows this insulating low temperature phase to high temperature metallic phase with 10 to the power 3 orders of magnitude change in resistivity, and a monoclinic to tetragonal structural transition. But compared to that, chromium nitride shows the opposite behavior. The resistivity at low temperature is actually low, so it undergoes a metallic to insulating transition as you go from low temperature to high temperature. So obviously the physics which really explained the transition mechanism in VO2 won't explain the transition mechanism in chromium nitride. And that is the point which Nicolas Spalding, about some years back, had tried to explain what is the origin behind this phase transition. So what she proposed with theoretical calculation is that in chromium nitride, what really happens is that as you come from high temperature to low temperature, first the spin alignment takes place. So a paramagnetic spins basically align into antiferromagnetic rock salt spin structure, but it's not just any orientation structure. You see there are two layers of ferromagnetic layer, two layers of two layers of another ferromagnet, but then they are opposite direction to each other. So basically 2 layer one direction, 2 layer other direction. And once you really create a structure like this, you realize that neighboring spins which are pointing to the same direction will basically will repel each other, and the opposite spin which are close to each other, they will try to come together, and as a result you will see a structural distortion. So the material undergoes an antiferromagnetic rock salt to antiferromagnetic rock salt to antiferromagnetic orthorhombic rock salt structural transition. And this, she explained with the help of magnetic stress in a material, and this magnetic stress is basically the first derivative of the exchange energy. So for a long time, this remained as a theory because people are not even sure that how to make chromium nitride, which reproducibly show metal insulator transition. So what we did is that we deposited chromium nitride on 2 substrates, in one case STO, the strontium titanate, and in one case MgO. In one case, we apply a compressive stress. In the other case, we apply a tensile stress. And then we grow this film at a very thin layer, 5 nanometer and 10 nanometer. And when you do this electrical measurement, as you can see, there's a clear trend in the shift of the MIT temperature. In the tensile strain, in the compressive strain, because the atoms are coming close to each other, your exchange energy basically increases, and that really pushes down, increases the Néel temperature. On the other hand, at the tensile strain on MgO, basically they reduce the exchange coupling, so that basically reduces the MIT transition temperature. So along with that, we did magnetic measurement also to verify that the MIT shift in the MIT temperature actually seen in magnetic measurement. And this is the direct 10 nanometer chromium nitride film on STO, which showed again as moved metal insulator transition from 270 Kelvin to around 320 Kelvin. We also measured exchange bias measurement to show that the low temperature phase is indeed an antiferromagnet, and the amount of antiferromagnetic coupling, basically the exchange bias, increases as you go to lower temperature. So having shown the structure, electrical transition and magnetic transition, we also demonstrated structural transition. As you can see at high temperature, this is MgO and this is the chromium nitride peaks. As you reduce the temperature, this basically splits into two, basically, first peak, second peak. And these are basically orthorhombic grains. Basically, this is orthorhombic transition. What is even more interesting is that it's not just two splitting. Each of the two peaks also have further split because of something known as structural twinning in the system. Because of the symmetry in the magnetic stress, chromium nitride, in one case, the distortion basically opens up the structure slightly from 90 to 91, 92 degree. In the other case, it contracts by 90 to 89 degree. So that is basically the demonstration of chromium nitride metal insulator transition and the mechanism of chromium nitride metal insulator transition. The second thing we looked at is basically, or as a consequence of metal insulator transition, what we found is that generally in most material, if you measure thermal conductivity as a function of temperature, thermal conductivity actually goes down with increasing temperature. And that's because of the Umklapp scattering or phonon-phonon scattering. But in case of chromium nitride, you see in case of bulk chromium nitride, as well as in chromium nitride thin film, it's the phonon thermal conductivity actually goes up. And that is quite anomalous because you can't use normal phonon-phonon picture to explain this behavior. So before us, theoretically it was shown that because you have a large spin-phonon coupling in case of chromium nitride, that may be the origin of metal insulator, this large enhancement in the thermal conductivity at high temperature. So we did inelastic X-ray scattering at Spring 8, Japan, that had its own technical difficulty because IXS is not that suitable for thin films. But eventually, as a function of temperature, we showed that as you increase temperature, the phonon lifetime actually increases. Acoustic phonon lifetime increases in chromium nitride. And since thermal conductivity is proportional to the acoustic phonon lifetime, the thermal conductivity, because the phonon lifetime increases, thermal conductivity also increases. This is for the acoustic, but optical phonon are not covered by or not impacted by spin phonon coupling, so the optical phonon lifetime actually reduces, just like in normal material. So this is the work on chromium nitride. This is the chromium nitride, where magnetic stress basically drive a structural transition. Magnetic stress drive a structural transition, and the structural transition basically leads to an electrical transition, and the consequences are felt in transport measurement. So let me now shift to the second example of metal insulator transition, or rather a photonic metal insulator transition in metal. This is the electron confinement induced plasmonic breakdown in metals. Again, plasmon resonance or plasma resonance, we all know. Plasmons are basically the oscillation of metals on conductive media. That is why you see metals typically giving color, if it's a goldish color or it's a silverish color. As when you work with plasmonics, you invariably try to engineer the plasmonic properties in a material so that you can increase this polaritonic resonance. Basically, you try to enhance the strong light-matter interaction in material. Generally, for most plasmonic research, if it's visible range plasmonic application, gold and silver have been the most important plasmonic material forever. Just because their plasmon resonance is so strong. But unfortunately, for practical application, neither gold or silver is structurally, gold and silver you cannot deposit in ultra-thin film form because they have a high surface energy. They basically aggregate. They are not stable at high temperature. You can't integrate with CMOS technology. And that is why for practical application, you really can't use gold and silver. What we have done is with some research, we have demonstrated that transition metal nitrides, for example, titanium nitride and hafnium nitride, are a very good replacement of gold and silver. So in this particular case, hafnium nitride, which is a 1-to-1 hafnium mononitride, when we deposit with a high quality, high temperature epitaxial growth condition, we showed that hafnium nitride actually acts as a very good replacement for silver for something known as solar mirror application. And this is shown in this particular case, reflection versus wavelength in the UV to visible spectral edge covering the entire solar spectrum. So this is the green one you see is silver, but hafnium nitride and zirconium nitride is actually operating almost as well. So in terms of numbers, silver has a 95% reflectivity in the visible spectral range or in the solar spectral range. and hafnium nitride and zirconium nitride has around 93 to 94% reflectivity. Then the solar reflectance, infrared reflectance are also very high in both the materials. So the question that we really wanted to answer at that particular point is that if you really want to use it for practical application, how thick a hafnium nitride or zirconium nitride do you need? And that really led us to really find a new physics in this domain. So this is basically the Drude model. So Drude model gives you the optical response of most metals, right? And Drude model is a semi-classical model where you basically look at the motion of an electron or any particle when you apply an electric field. From the Drude model, the plasma frequency omega p, which basically gives you the plasmonic response in a material, is given by carrier concentration times the electron charge square divided by the m star by epsilon infinity, which is the effective mass and the core dielectric constant. So as this equation shows, there is no mention of any dimensional parameter of your material. So it doesn't matter whether you take a bulk material with a centimeter size or a millimeter size or even a nanometer size. According to Drude's model, you should always have the same plasma frequency. But we really wanted to see that what happens if I reduce the dimensionality of a plasmonic medium to, say, 5 nanometer, 10 nanometer, or 2 nanometer. And again, that is the question answered by theoretician Igor Bondarev and Vlad Shalev, where they showed that if you have very thin metal film, then the optical response of this thin metal film not just depend on its own properties, but also depends on what substrate you grow the film and what is the superstrate. Most of the cases that is air. And the point that they try to always put forward that if you have a very thin film, ultra thin film, then the interaction between electron and electron in this ultra thin film is no longer can be explained by a Coulomb interaction. This interaction is much stronger, and you need to change the potential by something known as Geldish right-over potential. So they did some theory, and within the theoretical regime, they identified two regimes. One is transdimensional metal regime, where the material is still metal, but with some changes in the dielectric nature. More specifically, the plasma frequency now having a root d dependence on the thickness of the material. So plasma frequency is now a function of the thickness, d. But the second regime is basically a KR insulating regime, Keldysh right-over insulator regime, where plasmon resonance basically breaks down. In other words, there is no screening for the material. There's no material cannot screen any electric field in this case. And that has this very stringent requirement. Of course, if you can hit the experimental condition, then one should be able to see it. So what we did is that we first tried it with our titanium nitride. Titanium nitride is, again, looks like gold, acts like gold, and in fact we have developed it as a replacement for gold for visible range optical application. So when we reduce the thickness of titanium nitride from 10 nanometer to 1 nanometer, you see the material still remains its plasmonic characteristic because the epsilon ENZ crossover, epsilon near zero crossover, as we call it, still exists in all the material, but the plasma frequency is shifted, and that's basically the spatial dispersion of plasma frequency, which the theory predicts. But there is no plasmon breakdown. The localization is still not strong enough to basically cause any plasmonic breakdown. So the next thing we try to look at is what happens with hafnium nitride. As I mentioned in the last slide, for plasmonic breakdown to see, one requires a very stringent optical condition. So in case of hafnium nitride, this is the thick film. As you see, this is the ENZ at around 350, 340 nanometer wavelength. And as you reduce the thickness from 10 nanometer to 2 nanometer, you see there's a progressive reduction in the epsilon prime, which is the real component of the dielectric constant, from a negative value to a positive value, essentially underscoring a transition from a optically metallic regime to an optically dielectric regime. This shows up in macroscopic measurement of reflectivity and transmission. Also, in case of reflectivity, as you see, at 15 nanometer film shows a nice dip near the plasma frequency, but as you reduce it to 2 nanometers, sort of like flat, underscoring it almost like a dielectric nature. It shows here also. This is the 2 nanometer hafnium nitride film, looking perfectly as a dielectric. This is further verified by electrical transition, large change in electrical resistivity also. So as you reduce the thickness from a large 150 nanometer to a small 2 to 3 nanometer, you see the resistivity is increasing by 3 to 4 orders of magnitude, carrier concentration decreasing by 2 to 3 orders of magnitude, and temperature dependence of the resistivity also satisfies what normally you would expect, namely that for metal, the resistivity should increase with temperature in a metal, whereas for a semiconductor or an insulator, the resistivity should decrease with temperature. In this case, of course, because of the strong confinement, because of the strong localization effect, plasmon resonance basically breaks down. So that was our second demonstration of metal insulator transition in a transition metal nitride. And let me now tell you the third example that is driven by potential fluctuation in another semiconductor, nitride semiconductor, which is scandium nitride. So before I go to the physics behind it, let me just tell about just one slide about scandium nitride. It's a 3 nitride semiconductor. Instead of 3A nitride, which are gallium nitride, indium nitride, and aluminum nitride, this is a 3B nitride. It's a stable at ambient condition. And it's the only rare earth nitride, assuming, if you take scandium as a rare earth, that is stable at ambient temperature and pressure. It has a rock salt crystal structure, indirect gap of 0.9 eV, direct gap of 2.2 eV, a high melting temperature, similar to all other transition metal nitride. And the important point is that because of unwanted oxygen doping, scandium nitride typically has a very high carrier concentration of the 10 to the power 20. So we grow them in both MB as well as UHV magneton sputtering in our lab. They look perfectly epitaxial single crystal, and this is the electron band diagram for the scandium nitride. But now what we want to do is that we want to reduce this carrier concentration, because 10 to the power 20 is too high for any device application. And again, the strategy is very simple. You want to dope hole, right? So you can dope hole to reduce the carrier concentration. So if I take a normal semiconductor, let it be ionic semiconductor. So in this case, scandium 3 plus, nitrogen 3 minus. These are periodic potential, well-defined E versus K relation, energy versus momentum relation. But what really happens, once I take this base material, scandium 3 plus, nitrogen 3 minus, and randomly substitute some of the scandium 3 plus with magnesium 2 plus, because I'm hole doping, and nitrogen 3 minus, with oxygen 2 minus, this I don't do it. This happens automatically because of the impurities in the target, impurities in the source material, gas, and so on. Now, what really happens is that in this particular case, because of this random distribution of charged dopants in an environment where the parent material is 3 plus, parent cation is 3 plus, parent anion is 3 minus, and the dopants are 2 plus and 2 minus, you basically have a random potential fluctuation, because you can no way ensure that magnesium will be ordered in this system. And this random distribution of charged dopants basically leads to a large-scale potential fluctuation. And this is basically shown in this particular way. This is the real space diagram of conduction band and valence band. As you can see, the fluctuating potential basically changes the edges of the band. In some regions, you have conduction band underneath the Fermi energy. In some regions, conduction band over the Fermi energy. And there is a barrier which is known as percolation barrier. So if you really consider it as a simple picture, this particular system, highly doped, heavily compensated semiconductor, they actually act as if it's a dielectric material surrounded by metal bubbles in different metallic bubbles embedded in a dielectric host. And theoretically, it was shown some time back by Efros and Schrofsky. So we start doping scandium nitride with magnesium 2 plus. As you see, this is a resistivity versus temperature at when the doping level is very low. In other words, when the whole doping is very low, the resistivity is very low, and the resistivity increases with temperature, sort of like degenerate semiconductor or metallic. As you keep on adding more and more whole doping, the resistivity keeps on increases. And at the highest carrier compensation level, you see 10 to the power 9 orders of 8 to 9 orders of magnitude change in resistivity. And this is basically shown in this particular case at room temperature conductivity versus carrier concentration. And this purely happens because of the potential fluctuation induced carrier localization in this material. So at low temperature, if you we take log rho versus 1 over T, at low temperature, the transport is primarily hopping or tunneling, but at high temperature, the transport is mainly governed by the percolation of carrier over the top of the barrier. There is a simple way of understanding it. So it's just like if you have, if you try to fill if you try to fill water in a pond, and suppose you have all this, the pond bottom of the pond have all these fluctuating landscapes. So if your number of carriers is very, or number of water molecule is very higher than this landscapes, then you really, the landscape, the water flow from one side to another really don't care about this landscape. But as you reduce the number of water molecule, the water molecules basically get stuck in each of the individual puddles basically. So these are basically the metallic puddles, and at low temperature, the transport can only happen by tunneling from one puddle to another puddle, and high temperature, they basically occur because of the percolation. We use this to extract the parameters, use the transport measurement to extract the dielectric, to extract the potential fluctuation amplitude, and the transition where this carrier transition and the temperature at which this carrier transition takes place. Interestingly, as you can see, the mobility in this particular case actually increases with temperature. Mobility for most materials should decrease with temperature, but in this particular case, because in potential fluctuated metal semiconductor or potential fluctuated semiconductor, the mobility increases with temperature. The same thing about photoconductivity. So you shine light on this HC scandium nitride for some time, and then you leave it. In normal cases, you would expect the photoconductivity to drop in millisecond or microsecond, or at least in second orders of magnitude. Here you can see the photoconductivity just don't die. They keep on going on and on and on for 6-7 days up to in the lab. And the important point is that all of this happens while the material still is single crystal, because you are not introducing any geometric defect which is precursor for this Anderson localization. What all you are doing basically is, we are doing is basically you're changing the potential fluctuation, changing the potential by changing 3+ with 2+, and also supported by this transmission electron microscope showing their perfectly epitaxial single crystal nature in this. So one last slide before I end. What is the benefit of this potentially fluctuated or HDHC scandium nitride? And that is a sort of a remarkable thing that we have seen is the colloidal thermopower or the Seebeck coefficient. So what I have drawn here is basically Seebeck coefficient versus electrical conductivity. When the conductivity of scandium nitride is very high, so it's a highly degenerately doped, you see the thermopower or the Seebeck coefficient is of the order of somewhere between 30 to 100 microvolt per Kelvin. This unit is in volt, so microvolt per Kelvin. But as you reduce the conductivity by hole doping and create the potential fluctuation, we have reached a Seebeck coefficient of around 124 millivolt per Kelvin, which is in some organic material like C60 people have seen, but for inorganic material semiconductor, any type of semiconductor, this is probably one of the highest reports of a Seebeck coefficient in any type of material. We also, of course, looked at their electrical transport details in terms of conductivity versus temperature, Seebeck coefficient versus temperature, and I'm really happy to talk about it later if you are interested. So with that, let me end. So I think in summary, what I really want to mention is that nitrides have been really interesting and exciting class of material these days for various applications. And one of the things that was missing was basically a feature of metal-insulator transition, if you want to use it for some devices. What we have shown over our work over the last 3 to 4 to 5 years, is that we basically have developed now 3 systems where there are clear metal insulator transition driven by new physics. In one case, it is the magnetic stress, which leads to a metal insulator transition in chromium nitride, electron confinement in case of a metal like hafnium nitride, and of course the potential fluctuation in case of scandium nitride. So here are my group, and here are all the collaborators. Judith is here. We worked with her for chromium nitride project. So let me end, but before I end, let me thank His Highness because I work on a lab which is named after Sheikh Shakar Laboratory, and for the last several years, because of the generosity of His Highness, we have now established many facilities which has really helped us to progress in our research. So with that, let me stop, and I'm happy to take any question that you may have.